Hello and welcome back. I'm Adam with Push the Envelope, the channel that gives you everything artificial intelligence and machine learning. Today we are going to be going through linear regression, and in fact we're actually going to be making our own linear regression model from scratch. So this is going to be implementing some of the math and some of the background that we learned on linear regression into actual code, and we're going to be making our own model. Now, if you haven't learned about linear regression, then I have made a video going through the very basics, very high level of how it works, and we're going to be using that and piggybacking off of that in order to make our model today. So definitely, I'll link to it right now. Definitely go check that out before this video. But for everyone else who knows what linear regression is and is ready to get started, let's go ahead and jump over to the Jupyter Notebook. Okay, swapping over, you can see we are ready to go ahead and get started. First thing we need to do is start importing some packages. Now I'm going to be doing most of the heavy lifting using Numpy. So go ahead and import Numpy. I'm also going to be using matplotlib pyplot in order to view some of the data and some of the results that we're getting. And I'm going to be using sklearn to do some, in order to make our data and then to do some pre-processing on that data. I won't be using it to actually build the model, but this is just going to make it a lot easier for us to get some data sets and get the data ready to be fed into our handmade model. So from sklearn, we're going to be importing data sets. In addition to that, we are going to be doing from sklearn .model selection. We are going to be importing train test split. And that will take care of all the modules that we need. Go ahead and run that cell and we will go ahead and get started. Now, if you haven't heard of any of those modules, I do have tutorials on each one of these, but shouldn't be too necessary for this tutorial. So if you want to check them out, go ahead. I'll link to them right now, but you can also check them out later. You don't really need to know too much about them. First thing we need to do, we need to start making our data, and that's why we imported that data sets from sklearn. So I'm going to make a function called genData. And genData is going to be creating our data set. So data is going to be equal to data sets. And since we are doing linear regression, we need to make a regression data set. Datasets has a function called make regression. Easy enough. Now, what is it looking for? Well, it's looking for the number of samples. So n samples. For now, let's do 1000. It's going to be looking for some noise value. So if you remember before, if you've seen another tutorial, make moons also looks for a noise value, but that is a floating point from 0 to 1. This case, we are going to be importing an integer. So I'm going to make the noise equal to 20. Also, it's going to be looking for the number of features. For now, I'm just going to do 1. And the last thing, as always, I'm going to fix my random state to 1 in order to make sure that this is repeatable for you guys. Now, if you want to make this code a little more robust or whatever, you can go ahead and pass all of those into the function. I'm not going to worry about that right now, just because I know which values that I'm planning on using. I'm going to also just visualize the data. So I'm going to do a plt.scatter. I'm going to be, the first value is going to be data at 0. So I'm going to take the first bit of data. Now it's in a different form, so I have to transpose it, and then I also have to take the first one from that. So this is just taking the first feature, which happens to be the only feature in the data set. And I'm going to be mapping that against data at 1, which is all our output values. If I do a plt.show, we should be done here. Now, the last thing we need to do is obviously return that data in order for us to start processing it. So to call the function, I'm just going to have two variables, x and y, and that's going to be equal to genData. And the last thing we need to do is we need to split that data up into training and test sets for our model. So we're going to do x train, x test, y train, and y test is going to be equal to train test split, that function that we just imported from sklearn. Going to be passing in x, y it's going to be looking for a test size, which we will set to 20% of the data. And again, I'm going to fix my random state, so this is repeatable, to 1. Okay, let's go ahead and run that. I forgot an S up here. So in the datasets.make regression, make sure this says number of features with an S, plural. And as you can see, we now have a data set. This is actually quite a lot of data. I might reduce this down to 100 samples instead. Yeah, that looks a little better. It's just a little easier to see. You can make it 1,000. It's all going to work the same way. But we'll stick to 100 for now. Okay, we have our data. Now let's go ahead and start making our model. And to do this, I'm going to be storing this as a class. So I'm going to make a class called Linear Regression. Okay, so first thing we need to do in our class is we need to have our initialization function. So we're going to be defining init. And the only value I'm going to pass into it is rand. This is just a value that I'm making. I'm going to set the default to -1, and I'll show you what I'm going to do with that in a second. But it's back to fixing our random state. So if you want to use it, go ahead. You don't need it for this. I just want to make it, again, repeatable for you guys. Now, I'll scroll down a little bit. We do need to set some variables. So I'll do a self.weights. This is just defining our weights. I'm going to set that to none, just to have the placeholder in there, and then eventually we will be initializing our weights to some values. But for now, I want that to be none because I want to make sure that we have a value in there and that I can check to see if the weights have been updated or not. Same thing for the bias. So the bias is going to be equal to none. And the last thing I'm going to do is I'm going to store that random value. So self.rand equals rand. And that's all we're going to do for our initialization function. Now, like I mentioned before, we do need a function to initialize our weights, and I am going to do that by saying init weights. So defining a new function, init weights, and I'm just going to be passing it the x data. Okay, so the reason I imported this rand is because I want to say if self.rand does not equal -1, so the default is -1, which means I'm not going to be fixing the random state. But if it's anything other than -1, then we do need to fix the random state. And to do that, we're going to be using np.random.seed, and we're going to be passing in self.rand. If not, then it's not going to be fixing the random state, and we're just going to go ahead and continue doing a self.weights. And self.weights is going to be equal to np.random.rand for x.shape1. So we're going to take x.shape1, so the axis equals to 1, and we're going to define a whole bunch of random values to be the weights. Doesn't have to be random values. You can initialize them to 0, or you can initialize them to whatever you want them to be. I'm just going to go ahead and use random values. And I'm also going to be initializing the bias. I'm not going to do it the same way though. I'm actually just going to set the bias equal to 0. So it's going to be np.zeros. And that is also going to be x.shape1. And that takes care of our initialization function. I'm actually, just to make it a little clear, I'm going to call this function init weights and bias, just so I have both of those in there. Okay, now let's go ahead and start working through our fit function. And our fit function is going to take x and y values, and from there we can start working through the fitting of our data. So, first thing, like I said before, I want to see if the weights have been initialized or not. To do that, I am actually going to say if not self.weights. So if this is none, then we're going to be going into this. We need to call self.init weights bias, and again that's looking for x. Okay, that takes care of initializing our weights. Now we need to go through however many iterations we want to, and I'm actually going to make that a parameter that you can input into the fit function. It's going to be the epochs, and I'm just going to default that to 10,000. Okay, so that's however many iterations that we're going to go and train our model on with the training data. How many times we're going to go through the training data. Now to do that, we're going to do a for loop. So for epoch in epochs, what are we doing? First thing we need to do is we need to get the predicted y values, the y hat values. So that value is going to be called y hat. And that is going to be equal to np dot dot. So this is the dot product of the input data, which is x. So these are x. So however many features we have, we're going to be doing a dot product of those and the weights. Right, so just multiplying them all by the weights, and then adding in that self dot bias. This gives us the function of our line. And it's plugging in all the x values into the function of the line and coming out with whatever the predicted y values are. Now, once we have those, we can determine how far off we were and adjust based on the gradient. So we can define the gradient of the weights. And this is going to be equal to 1 over the number of data points that we have. So this is x dot shape at 0. This is the number of training data points that we're passing in. And we're going to multiply that by np dot dot the x values, but we need to transpose them. So x dot t. And then we are going to be doing the dot product of that versus the y hat values, the predicted values minus the real values. So the difference, so this is the error between the predicted values and the real values. And that will go ahead and take care of the gradient for the weights. Now we need the same thing for the gradient for the bias. This, however, is going to be equal to, again, 1 over x dot shape 0, 1 over the number of points that we're training on, but it's going to be equal to that times np dot sum, so the sum of the errors, so y hat minus y. Just taking all the sum of the errors, and that is going to be the gradient for our bias. Now that we have that, we can go ahead and update our weights and biases. So self.weights is going to be equal to the self.weights. So I'm just going to do a minus equals. So the weights minus the gradient for the weights that we just came up with times a learning rate, which is, again, another parameter that we're going to have to pass into the function. So I'm going to jump to the top and pass that in. I'm going to default that to 0.001. Okay, so the gradient times the learning rate, we're subtracting that from the weights. We're going to do the same exact thing for the bias. So bias minus equals gradient of the bias times the learning rate. And that's it. That's how we train our model. So I do want some other things. I want to know how the loss is progressing over time, and maybe I want to just plot that loss. So we are going to be using, again, this is regression. So we want to know how far away are our lines from the real values, right? So how far off we are. And I'm going to do that by coming up with a new function called mean squared error loss. So MSE loss. And this is going to be taking in the real y values and the predicted y values, the y hat values. And it's going to be returning np.mean. So we're going to be taking the mean of the real values minus the predicted values. And then we're going to be squaring those. So mean squared error. We're squaring the errors and taking the mean of them. Okay, now that we have that, we can come back down to our fit function, come up with a value called loss, and that's going to be equal to self.msc loss, passing in y and y hat. That will give us our loss values. I do want to record the loss over time, so I'm going to come up right before the for loop, make another variable called losses as just a empty array. And we are just going to do losses.append loss. Every time we train the data, we're just appending whatever the loss was, so we can see how it progresses over time. Okay, other things that I want to see is maybe, after a few epochs, I want to see status messages just to make sure that it's progressing in the right way. So I don't want to see it every time because I do not want 10,000 messages. So I'm going to say if the epoch plus 1, because the epoch is going to start at 0. So if the epoch plus 1 is, if I take the modulo of that, of the epochs divided by 10. So I want to see only 10 status messages is pretty much what I'm saying here. And so this divided by 10 is going to figure out whatever that value is that I need to take the modulo of. And so that if whenever that's equal to 0, I want to print the status message. I also want to print it if I am at the very last epoch. So I'm going to add another one so I'm going to put or if the epoch is equal to epochs minus 1. So if the current epoch is equal to the last epoch, then go ahead and print this message out as well. All right, so we are going to be printing the epoch, and this is going to be equal to, all right, let's do the string of the current epoch plus 1. And we're going to be adding in a division sign. And so I just want to say the current epoch over the total epochs. So that would be the string of epochs. Okay, that takes care of which epoch that we're currently on. I also want to know the loss. So I'm going to just put a little divider in here. And this is going to be equal to loss. All right, and the loss is going to be, we made that variable, so just pass in the loss here. And that is going to be all for our status message. Last thing I want to do is I want to graph that those losses over time. So outside of the for loop, at the very end, we're going to do a plt.plot. This is going to be the range, the length of losses. And then we're going to be graphing the actual loss values. Do a plt.show. And that should be it for our fit function. Okay, so that takes care of training our data. Last thing that we need to do is we need to come up with a prediction function. Now that we have it trained, how do we know that it's working, or how can we predict future points? So define predict. Predict is going to take the x values, and that is it. Now, if you remember way up here at the top, this gave us our predicted values. So the dot product of x times the weights plus the bias. So that's how we're going to be making our predictions. I'm going to copy this down here, paste it straight in here, and that's it. That's all for the prediction function. All we have to do is return the y hat values. And that takes care of our entire linear regression function. Super basic and super easy to implement. Now let's go ahead and make sure that we implemented it right and make sure that it works. To do that, I'm going to define a classifier. So CLF is going to be equal to linear regression. This is the name of our class that we just made. And if you go back up here to the init function, random value is automatically assigned to -1, which means we are not going to be fixing the random state. I, however, want the random state to be fixed, so I'm going to pass in rand equals 1. Next, clf.fit. If you remember, I'll scroll up to the top. We have already split out our data into training and test sets, so it should be easy to pass those in. So I will pass in X train and Y train. Other things you can pass in the amount of epochs or the learning rate. I'm just going to use the default, so I'm not even going to worry about passing those in. Go ahead and run that. I do have an error. So for my for function, instead of saying for epoch and epochs, I do need to say in the range of epochs. And go ahead and run that, and you can see we have gone through 10,000 iterations. You can see the loss is slowly going down, and that's very visible by this knee in the graph right here for the loss function. So we have trained. Let's see how well we have actually done on the data. And we're going to be using the predict function that we just made. So our predictions are going to be equal to clf.predict, passing in the x test values. Okay, so passing in the x test values, we're going to get the predicted y values. Now we are going to print mean squared error loss. And if we go back up here to this function, I'm just going to pull everything that we were returning. And we're going to use that as what we're printing out for our loss. And instead of y, this is going to be y test. And y hat is now called preds. So we're taking the difference between the real y test values and the predicted values for x test, squaring them, taking the mean, and then printing that out to the screen. And that gives us this loss right here, 386. Doesn't really tell us much. What will tell us more is if we could visualize the line. So let's go ahead and do that. Again, we're going to do a plt.scatter. I want to print all of the points. So x.transpose. We're going to transpose the data, take the first feature. And we're going to graph that against y. Now, that gives us all the data. If I do a plt.show, you can see that's all of our initial data. But I want to print the line that the function or the classifier regression model was able to come up with. So I'm going to make an x range variable, and that's going to be equal to np.array. So we're going to make a numpy array of the. I just want to know how far over is the minimum value on the x, and how far over is the largest value for the x, because that's where I want my line to start and end. So x.min by x.max. So two variables in here. Takes care of the x values that we're trying to plot. Now we need to do the same thing for the y. So y range is going to be equal to the classifier dot weights times those x values, so x range plus the classifier dot bias. Again, the equation of the line, the slope, which is in this case is the weights, times the x value plus the y-intercept, or the bias in this case. And all of that is going to give us the line. So let's go ahead and do a plt.plot. We're going to be plotting x range versus y range. And let's go ahead and make this red just so we can see it. And plot. And there you can see we have the line that the linear regression model came up with. And it looks pretty good. It's probably where I would put it as well. So you can see that it's working for this. Again, this is a super easy problem. I only did one feature. You can up the amount of features. This classifier will still work. It will be harder to visualize, I'll say that. But the harder problems are harder to visualize because we work in dimensions that we're not able to comprehend as humans. So that's all for the linear regression model. I'm going to be using this. I'm not going to be using the one I just made. I'm going to obviously be using sklearn just because it's so much easier. But there are future problems that I'm planning on using these for, so stay tuned for those. If you got anything out of this, please go ahead and like the video. I'm going to be doing more of these. I think the next one is going to be the logistic regression model. So if you enjoyed kind of sitting down and making these by hand, definitely check those out. I have other ones as well. And I've also done a neural network one, which goes a little more in depth than just these simple gradient descent models. So if you got anything, please like the video, subscribe to the channel for more stuff like this. But that's all, and I will see you in the next video.